So in the next section, we're going to be talking about how to take a power series and try to see it as a function. So it's kind of, it's one thing to like be given a function and then turn it into a power series. It's another thing to be given a power series and try to turn it into a function. Does that make sense? Like a function that's not just a power series rendition, okay? So, for example, last time we did this one right here, okay? And I said that it has something to do with a power series that we already know. You remember like a logarithm of 1 plus x, logarithm of 1 plus x. What was the power series for that? Do you remember at all? Do you guys remember? Wasn't it like x minus 1/2 x squared plus a third x cubed minus etc. and it like kind of went every other term that way? Yeah? And so if I were to write that in summation form, it would be sum. Let's see here, n going from 1 to infinity. I don't know, maybe like minus 1 to the n minus 1. Now let me write it this way just to make it a little bit clearer. Minus 1 to the n minus 1, because it looks like the minus sign is one off from, like for instance, if I'm to the first power, I don't want to do minus 1 to the first power because that would be a negative sign, yes? So it's kind of one off from that, so I'll go minus 1 to the n minus 1 over n x to the n, okay? You might say to yourself, okay, what does this number 3 series have to do with this function? Well, it turns out I can kind of tweak this thing to have the appropriate form, okay? The way that I would do that is the following. So first of all, I'd like to see a minus 1 to the n minus 1 pop out. I can actually do that. This is going to look kind of weird, so watch this. This is sum n going from 1 to infinity. I'm going to write this as minus 1 to the n times 3 minus x to the n. What did I just do from each one of the factors of x minus 3? What did I just factor out? A negative 1, okay? And then I can kind of rewrite this. I could pull out a minus sign and just say, okay, minus sum n going from 1 to infinity minus 1 to the n minus 1 over n. And then this is 3 minus x to the n. Now stare at these two things for a minute. Do they look basically the same? What's the only difference between those two things? What's that? There's a minus sign out front, and what else? 3 minus x has replaced x. Do you know what I'm saying? So I'm telling you, this thing is going to be equal to minus logarithm of what? 1 plus, looks like I've replaced x with what? 3 minus x. Okay? So that's what's going on here. So this thing is minus logarithm of 4 minus x. And do you guys remember what was the radius of convergence for this thing? We did this last time. What was the radius of convergence for this thing? 1. Okay. What was the center? Remember what the center was for this? By the way, you can tell what the center is just by looking at the powers. What is the center? It's not 0, the center is 3. And what is the interval of convergence? Last time we messed with this, right? We plugged in, right? We were looking at the interval from 2 to 4. We were going from 2 to 4, 3 is at the middle. We go 1 in either direction of 2, down to 2 and up to 4, yes? And we discovered that we are not allowed to plug in 4 because we would get the alternating, or we would get the harmonic series, but we are allowed to plug in 2 because we get the alternating harmonic series, which converges. Yeah? So we got the interval of convergence 2 to 4, okay? And so then when we stare at this for a minute, and we say, oh, look, this thing really is just the logarithm minus the logarithm of 4 minus x, we say, oh, yeah, of course I can't plug in 4. You know what I'm saying? You can't plug 4 into that. 4 minus 4 would be 0, and you'd have logarithm of 0, which makes no sense. On the other hand, I can plug in 2. You see? I actually can plug in 2, and I'm going to get log minus the logarithm of 2. And in particular, we can kind of see that we're going to get kind of a formula for the alternating harmonic series based on that. Remember I told you that the alternating harmonic series actually adds up to logarithm of 2. Remember I told you that? So look, if you plug in x equal to 2, look what happens. Remember there's a minus sign sitting right here. If you plug in x equal to 2, like the minus signs, you can kind of cancel those. And you'll get that if I plug in x equal to 2, we'll get the alternating harmonic series, and we'll get sum n going from 1 to infinity minus 1 to the n minus 1 over n is equal to logarithm of 2, which is sort of weird, right? Natural logarithm of 2 by plugging in x equal to 2. And by the way, I kind of wanted to show you, any questions on that, by the way? That's sort of tricky to reverse engineer a function from the power series, but I'm just saying you can do it. Most of the times you're going to be asked to do this, it's going to be a lot easier than this one. But I'm just saying it is possible a lot of times to reverse engineer a function from a power series based on things that we know power series expansions for. But any questions on this before I show you like a little visual rendition of what's happening here? Okay, so watch this. Let me erase this. Okay, let's go over here. I think I had this thing kind of laid out in here in Desmos. Yep, right here. So watch this. Here I have minus logarithm of 4 minus x. That's the green curve. Do you see that? Minus logarithm of 4 minus x. And then this purple curve, I've kind of put in the function here, sum m going from 1 to up to n. And of course, I'm taking better and better approximations of this. I didn't plug in the entire power series. But you see, like if I let this thing catch up, look, it's a really good approximation between 2 and 4, and then something starts to go wrong at 4, it looks like, okay? And it's definitely going wrong at 2. That's very obvious, okay? Okay? So you see this thing is very good approximation between 2 and 4. And at 2, it looks like it's not too bad. But if I get below 2, I end up kind of taking off away from the green curve a little bit. So I at least wanted to show that to you. Any questions on that before we move on to other matters here? Any questions? All right. So let's continue looking at these things. What about the next one? Now remember, I want you to tell me like what the radius of convergence is. I want you to tell me what the center is, and I want you to tell me what the interval of convergence is for each one of these things. And in particular, I want you to look at number 4 here. Okay, so that one's a little bit messy, but that will involve either using the root or ratio test, if you will recall. And then we'll be able to figure out, hopefully, a nice radius of convergence, a center, and an interval of convergence, okay? So work on that for a couple minutes, and then we'll kind of reconvene here. Okay. Help me out here. How did you guys start this out? Ratio test? Yeah. So if you call that whole thing AN, right? And you apply the ratio test, then you're looking at the absolute value of AN plus 1 over AN. And that's going to be, okay, first of all, I can ignore the -1 stuff, correct? Since we're taking absolute values anyways, okay? And what am I going to end up with? Like, you know, absolute value of x to the 2 quantity n plus 1. Is that right? Over, what's on the bottom? Right, 2 to the 2, I'll say to the quantity n plus 1 times, okay, this last one, I'm a little bit more, okay, n plus 1 factorial squared. How do you suppose, what would be a smart way to write that? Yeah, n plus 1 squared times what? N factorial squared, right? Because n plus 1 factorial squared would just have a couple factors of n plus 1 to turn the n factorials into n plus 1 factorials. But then all of this is divided by basically the same thing, except it's absolute value of x to the 2n divided by 2 to the 2n times, what is it, n factorial quantity squared? Yeah? So I have a lot of cancellation that happens. Like what? Like what cancels? Yeah, x to the 2n basically cancels that, because like if you think about the 2 sort of distributing here, right? You're just going to have an x squared left. Now what about the 2 to the 2n? Those cancel, right, for the same sort of thing. This 2 kind of distributes in here. And what are you left with? Just 2 squared, which is 4. Okay? And these guys cancel completely. Okay? So what am I left with? Yeah, absolute value of x squared over 4. What did you say, Drake? Right. And then what do we have to do with this thing? Take the limit as n goes to infinity. Now here's the thing. No matter what x is, I don't care, even if it's 30 trillion, it's still a constant. Do you know what I mean? And if I let n go to infinity, that bottom is going to overwhelm whatever x is. So what do I get as this limit every time? 0. Wow, which is less than 1. So what do I do with that? What does that mean about the radius of convergence? That means that I can plug any x value in, right? Right. So r is equal to plus infinity because I can plug any x works, right? Any x works. Okay. So the interval of convergence is just minus infinity to infinity. And of course, what's the center of this thing? Yeah, right, because they were powers of x. They happen to be even powers of x, but they were powers of x nonetheless. Okay, so that's c is equal to 0. Okay. Now I'm going to be honest with you. It's hard to discern what function this actually is. I actually don't know. Okay. It looks kind of like what was something that had only even powers? We saw something like that before, like alternating even powers. You guys remember? It was cosine, right? So the closest thing we would have to something like this would be cosine. This thing is fairly messed up because it has all these squared factorials in it. Does that make sense? That's not what we had in the case of cosine. Now there might be a way to sort of tweak this so that it does become that, but we just don't have enough functions in our back pocket to be able to say what this power series equals. But we were still able to say this power series converges no matter what x value I plug in. And it is a function of x. Okay? It's just kind of a weird one. Okay? Any questions on that? Okay, that's interesting stuff. So let's do this next one right here. This thing is a little bit messed up because it's cut off on the bottom here. So let me escape out of that so you can see it better. Okay. So -3 to the n, x to the n is starting from 0 and going to infinity. and you have the square root of n plus 1 at the bottom. By the way, in the last problem, I didn't have to check any endpoints. Do you know what I'm saying? Because there weren't any. The thing just went in both directions forever. The interval of convergence did. But that's not always the case. Sometimes we do have to check endpoints. So why don't you look at this one for a couple of minutes, and we will reconvene thereafter. All right. Did anybody use the root test? You used it? Okay, you tried. Well, let's make it work, my friend. So let's see. I want to do one that's like slightly different. Okay. So hang on. Let's actually go over into the whiteboard. Okay. So let's see here. So what was it? It was somebody kind of read it off for me again. N going from 0 to infinity. Was it -3 to the n, or -3 to the n? X to the n over the square root of n plus 1, right? Okay, so what do? We call this like an. Jared, you said you tried. Well, what happened? Yeah, okay, so you took this to the 1 over n, right? Yeah. And what you're saying is you kind of combine the -3 and the x under 1 power, and you wrote n plus 1 to the 1/2, okay? So, by the way, if you take the absolute value of the -3 to the n, the minus sign just goes away. Do you know what I'm saying? So what you're saying is you wrote this as like basically 3x to the n over n plus 1 to the 1/2, all raised to the what, Jared? Okay, and the top part, that, that's pretty convenient, isn't it? Yeah? The top part, what does that go to? 3x. By the way, I better put absolute values here, right? So absolute value of 3x, once I take the nth root there, and then what about the other thing though? It's going to be n plus 1 to the what? And then you said, oh man, if that were just n to the 1 over 2n, we'd be good to go, right? But it's not quite that, but watch. I think we can tweak this a little bit. Okay, so let me write this as okay. Let me write this as okay. I'll write this as n plus 1 to the 1 over n plus 1. Okay, all raised to the n plus 1 over 2n. I mean, look, at those powers multiplied together, wouldn't you just end up with 1 over 2n? Do you see that? Look, if that power multiplies by 1 over n plus 1, the n plus 1's just canceled. Do you know what I'm saying? Okay. And what does this go to as n goes to infinity? Now like the n plus 1 matches 1 over n plus 1. What do we know about the nth root of 1 over n as n goes to infinity? It doesn't really matter if I replace n with n plus 1 because they're both going to the same place, right? What's that thing inside going to go to? 1. What's n plus the power, n plus 1 over 2n? What does that go to as n goes to infinity? 1/2. So the bottom goes to 1 to the 1/2, the square root of 1, which is 1. Okay. So what do we get? Absolute value of 3x over, 1 to the 1/2, which is sort of silly. That's just the absolute value of 3x. And what do we want to be true about this limit? This limit needs to be less than 1. Well, that happens, right? So we need this thing to be less than 1 to get convergence. Okay? But if the absolute value of 3x is less than 1, that just means that the absolute value of x, what does that mean about the absolute value of x? What does that need to be less than? A third. You just divide through by 3, okay? So that means x is trapped between where and where? Positive and negative a third. What is the center of this, by the way? We should have been able to say this from the beginning. The center is 0, okay? What is the radius of convergence? Think about it. Look at what we just came up with. What's the radius of convergence? A third. And now we're working on the interval of convergence, which is going to require that we plug in some endpoints, yes? Okay, so what if I do plug in some endpoints? What are the endpoints of the interval? Yeah, so if I plug in negative 1/3, watch this, this is interesting, think about it. If I plug in x equal to negative a third, what is going to happen? You're going to have -3 times negative a third, both raised to the end, the negatives cancel. Do you know what I'm saying? And so what do we end up with? The sum in going from 0 to infinity of 1 over the square root of n plus 1, which you suspect behaves like what? 1 over into the, or it behaves like a p-series, and in fact, by the limit comparison test, it will, yes? Will behave exactly like, in fact, I mean, think about it for a second. This really is, not joking, this is just the series in going from 1 to, think about it, if you started at 0, the first term is 1 over the square root of 1, right? The second term is 1 over the square root of 2. So really, this is like the same thing as the series in going from 1 to infinity, 1 over the square root of n, which this thing converges. Or no, it doesn't. What does it do? What am I saying? Diverges. Right, it's a p-series with p equal to 1/2, yeah? What about the other endpoint? Except what happens with the minus signs this time? The 3 and the 1/3 will cancel. Yeah. Sum n equals 0 to infinity, minus 1 to the n. There's a minus 1 that survives, yes? And that's over the square root of n plus 1, which, by the way, if I were to shift this thing, I could say it's just n going from 1 to infinity. I don't know, minus 1 to the n minus 1 over the square root of n, which what's up with that series? It's alternating, and the terms without the alternation decrease to 0. Therefore, what's the conclusion for this guy? Converges by what? By alternating series test. So what is the interval of convergence here? Okay, it's going to start at negative a third and go up to a third. Do I include negative a third? No. Do not include negative a third. Do I include a third though? Yes. Okay, so that's interesting. So this time I exclude the left endpoint and I include the right endpoint. Incidentally, there are times where you include both endpoints. Okay, that will happen from time to time. Okay, any questions on that? So that time we actually applied the root test as opposed to the ratio test, just to kind of mix things up a little bit. Yeah, Daniel.
With the ratio test, at one point I got -3 and -3 to the n times -3 times x to the n times x all over n plus 1 plus 1, and then parentheses around that. Half. And so can you distribute in the denominator of that? Can you distribute the 1 half to the n plus 1?
No, what you're going to have is you're going to have basically a ratio of square roots. You're going to have, because the one on the bottom will flip up from an, and you'll have square root of n plus 1 over the square root of n plus 2, basically, which you could write as one giant square root of n plus 1 over n plus 2. But n plus 1 over n plus 2 just goes to 1 as n goes to infinity. So that would just go to the square root of 1. So it would be a similar kind of calculation to what we did here. Okay? Right, distribution of powers across the sum is not permissible. Other questions on that? Yes. I just did it because this was annoying, Sean. See this right here? Like that doesn't match up with this. What I was more hoping for was like not an nth root, but an n plus first root. So all I did was create it. Just by kind of saying, oh, well, I'll write it as 1 over n plus 1 and like multiply by n plus 1 over 2n. Like I still have to keep that 2n around. Yeah? So I just wanted to see a root that was the same as the base, because I know what the limit of that thing is, just 1. Okay? It's a good question. That's just a little algebraic trickery. Okay? Probably, I mean, the ratio test works well too. I mean, it all works out the same, but I just wanted you to see the root test rendition of this. Okay, other questions? Yeah, okay, well, let's get back to business here. Okay. All right. So there's a lot of words on here. Words. Okay. So again, you have a power series, you have a radius of convergence, you have an interval of convergence from C minus R to C plus R, and you might include the endpoints, yes? Okay. But then the question is, what happens if I take derivatives of the power series? Like the whole point of this is like, it's really fun to work with polynomials as opposed to some other obnoxious functions, right? So we would rather turn functions into power series if we can. Why? Because we want to be able to take derivatives, okay? And integrate easily, okay? So like for instance, of course, if I take the derivative of a power series, notice, I mean, all you have to do is what? Notice what happened to the derivative. What did I do? Like there's nothing deep going on here. What happened when I took the derivative? Basically, that power just came down there, yeah? And basically what this is saying is you're allowed to take derivatives of power series the way that you think you should be able to. You have to be careful because it's an infinite sum now, right? But you can go to each term and just take the derivative separately and just decrease the power by 1. Of course, when you do that, the constant term A0 just goes away, okay? And you can integrate term by term. That's what number 2 is saying. So number 1 is saying you can differentiate the way you think you should be able to. And the second part is saying you can integrate the way that you think you should be able to, okay? You can just integrate term by term. Add 1 to the power, divide by n plus 1, and there's your integral. Of course, you have to have a plus c here, which is slightly annoying, yeah? And then there's a question about the radius of convergence. Well, guess what? This is what's so amazing. The radius of convergence is the same for the derivative and the integral of the original power series. So the only thing you'll have to potentially check is, what do you think? The endpoints. You will have to check the endpoints if they exist. That could change, okay? But the interval of convergence itself, except for the endpoints, remains intact when you take derivatives and integrals. Okay, this is very important, so you don't have to like redo a bunch of work. All you have to do is check the endpoints for convergence, and that's the most your interval of convergence can change by. Okay, any questions on this? This is not, there's a lot of words on this slide, but all it's saying is you can take derivatives and integrals of power series the way you thought you could, okay? And the interval of convergence basically stays the same, except potentially where? The endpoints. And you might have to check the endpoints. That could get a little messed up because in the case of the derivative, you're slapping on a factor of n. Does that make sense? That could mess things up at the endpoints. And actually with the integral, you might actually be helping at the endpoints because you're dividing by n plus 1. Yeah? That could actually make the terms go to 0 faster. Okay? But by taking the derivative, you slap on a factor of n, which could make the terms go to 0 slower. Okay? So you can kind of think about that when you go to Chuck's this afternoon for your lunch, okay? What I'm gonna do next time, at the beginning of next time, we'll work through this example where we actually start with this power series, which by the way is really just a logarithm power series in disguise again. You see it? Think about it. Let me write this to the n minus 1. This is literally the logarithm power series again. But what have I done? I don't have to use plus 1, I can do minus 1 also. This really is, I'm telling you, just logarithm of 1 plus, what do you think it is? It's not 1 plus x, it's x minus 2, okay? In disguise, but we'll look at this thing, its derivative, its second derivative, and its integral. We'll play around with that a little bit. That's it.